Models in TinkerCell are constructed using components from this catalog of biological components, which includes reactions, different types of regulations, DNA parts, molecules. Components from this catalog are placed on the screen by either dragging and dropping, or by clicking it and then clicking multiple times on the screen to insert multiple components. Now I can press escape or space to exit the insertion mode. Connections or reactions are inserted in the same manner. You can drag and drop a reaction, or you can take existing items on the screen and create reactions using them by clicking the components on the screen. Once a network is constructed, it's analyzed using one of these programs in this Programs menu, which is available on this right-hand side as well as here and also here. Users with programming experience can use Python scripts to actually write small programs here, Python or Octave scripts. Alternatively, you can use this coding window to write Python or Octave scripts, and all the functions are listed in this coding window. Now, let's construct a simple enzyme catalysis network. So I'm going to drag and drop a one-to-one reaction. I'm going to drag and drop an enzyme, and then under regulation I'm going to select regulation and then click enzyme and then this reaction. So TinkerCell actually recognized this a specific type of regulation, which is enzyme catalysis. Notice it placed this enzyme catalysis button here, so I can drag and drop enzyme catalysis to create the whole reaction. Now in the console window, if I type the name of this reaction, which is J1, I can press tab for auto completion. So if I type the name, it shows me the reaction rate formula, the participants, which is the catalyst, reactant, product, the stoichiometries, the parameters, and the type, which is enzyme catalysis. Additionally, in this model summary window on the right, you can look at the rate equation and all the parameters, as well as change them. I can also double click on this reaction to look at the rate equation as a function of different variables, as well as the reaction stoichiometry and the parameters. Now let's do a simple simulation. I'm going to click on Simulate Deterministic Simulation. A window pops up here asking me for the end time, step size, and so on. And I'm going to turn on sliders here. So there's a simple simulation. Now the sliders allows me to change the value of different parameters and actually observe the change in the simulation. Now let's construct, so the results of the simulation are also printed on the screen, and I can press escape to clear it. Now let's construct a simple genetic network. So I'm going to put a coding sequence on the screen, and then an inducible promoter, and then go to reactions, click on one-to-one, click on coding, and then the screen. So TinkerCell automatically recognizes that a protein is made from a coding segment, so it recognizes the fact that this is a so again we can type the name of this reaction, PP1, and it recognizes this as a protein production reaction, and it shows again the stoichiometry and rates. So currently the rate is just constant, so if I double click, it's just a constant. Now if I put this promoter here, and then if I add a regulation, let's see, transcription activation. Well, it's an inducible promoter, so I have to activate it. Now, if some of these regulations are not available in this catalog, you can go to Options and then Show Hide Catalog Items, and you can show or hide any of the items in this catalog. So I select transcription activation, I click on the promoter, and then anywhere on the screen it creates a transcription regulation. Now if I look at this reaction rate, notice that TinkerCell has edited this reaction rate so that it's a function of, it's a hyperbolic function of the transcription factor. And if I change the parameter in this transcription factor, the Hill coefficient to say 4, then this is going to be a sigmoidal function. And again, I can simulate this. Let's turn off sliders for this one. And you'll see, well, since the protein's now getting degraded, it keeps building up. And in this plotting window, I can turn off any of the items that I don't want to see. And I can choose log scale, change the colors, and so on. Now I can also choose to keep the previous graph. So if I keep the previous graph, what will happen is, let me add a degradation term here. So degradation and then reaction. And then simulate. So when I kept the previous graph, it obviously didn't delete the old graph, it kept both of them. So there's the new graph with degradation. As you can see, protein doesn't build up. And append to current graph, what that does is, if I simulate, it will actually draw on top of the current graph. So it drew on top of this graph here. Now I can also color some of these items.